the name of my talk is actually.
We can see your presenter view instead of the original view.
Okay, is my presenter view visible?
Yeah, your presenter view is visible.
Is that okay?
And that's okay, yeah.
So the name of my talk is on composition of multipartite quantum systems, a perspective from the time-like paradigm. So these people have actually worked on this particular paper. So right now it's in archive. So Manik Banik, Edwin, Samrat, Ramkrishna, me, Tamal, Som, and myself. So before actually going towards the actual content, so let me give some motivation. So we know that our everyday objects are fundamentally made up of some constituent objects. So this composition is a very clear idea in our mind. So even daily like objects, we know it's made up of some constituent elements like nuts, bolts. And not only this, some really advanced technology. Here also we have some idea that it is made up of some fundamental objects. So, but not all kinds of compositions are allowed in nature. For example, if you have a look at these ones, so even a 4 or 5 year old kid might say there's something wrong with these pictures, and these are actually not possible in reality. So this work actually tries to address this question from the context of quantum mechanics. What kinds of compositions are allowed? So briefly, let me tell you what is the outline of the talk. So firstly, I'll discuss a bit about generalized probabilistic theories, then what are the composition rules in this framework, then the same thing but for quantum systems, how do we generalize this for quantum systems. Then I'll talk a little bit on this space-like and time-like correlations. Then we'll move towards a particular game which will actually help us guide us towards the result, and then finally I'll move on to conclusions. So in generalized probabilistic theories, every system is actually a three tuple given by this, where we have some collection of preparations, some collection of effects or observables, and some dynamics on the system. So in this work, we won't be actually considering the dynamics section that much. We'll just look into the prepare and measure scenario where some preparation device prepares some state of the system, and you are allowed to do some measurement on the system. All right. So let me give some example. So this is the standard square bit model. So which is very well known. So here we can see that this blue color square is constructed to be some state space, and here, so in this framework, every state space, we can think of it as some convex set being embedded in some Rn. And similarly, we have some effect space. So this effect space, again, it's some convex set. It is created from the state space by looking into set of all possible vectors in this Rn that will give us some valid probability on all possible states. So again, we can think of any effect as some functional on this state space, which maps it to some 0,1, closed interval 0,1. Again, so this framework, we actually have to define how this action will take place, this action of the effect on all possible states. And once we have defined all these things, then we can talk about this measurement. So any measurement, we can think of it as some partition of a unit effect. So again, here we can see a unit effect, and a measurement is basically some partition of unit effect, where the unit effect is some sort of effect where actually which gives us one probability for all possible states. And lastly, we have the transformations. So even our standard quantum mechanics, we can think of it as a generalized probabilistic theory. For example, the C2 system, our state space is the block sphere. Again, we can embed this in some Rn and talk about this quantum mechanics in this GPT framework. So once this is clear, let me briefly discuss how do we talk about joint systems in GPT framework. So suppose we have two systems, SA and SP, which are described like this. So the composite system, SAB, the question is, how do we define this omega AB and EAB for the composite system? So we will demand some natural conditions, like obviously the states and effects here should be such that they should give us valid probabilities. Not only that, we will obviously want a theory to satisfy no signaling conditions. So the usual no signaling conditions will impose. And apart from this, there's something called as local tomography. That means if a state from the system is shared between two space-like separated parties, then the parties will be able to locally tomograph the state. So under these conditions, we can see that only some sorts of compositions are allowed, which actually lie between what is known as the maximal and the minimal tensor product. The maximal tensor product corresponds to allowing only product kind of effects and then asking the question, what kind of states are allowed in this theory? By allowed, I mean that they should give consistent probabilities for all sort of product effects. And similarly, the minimal tensor product is the converse, where we just allow product kind of states or separable kind of states in the theory. And similarly, we construct the effect space for this theory. So once this is clear, let me go towards the same composition rule, but now let's assume both our systems to be quantum systems. So suppose we have two quantum systems, that is the all possible dynamics, all possible measurements in states for this system are defined by some Hilbert space, and similarly for this. So usual quantum mechanics holds for system A and system B. Only thing is, now we are not assuming any sort of composition for this. Usually in quantum mechanics, a postulate says that, okay, so the composite system should have HA tensor HB as the composite Hilbert space, but we are not taking that assumption here. So what possible things are allowed here? So there is something called as sep composition. So where we just allow product kind of or a separable kind of states. So here pi corresponds to some positive operator on the Hilbert space of A, and pi b is similarly for Hilbert space of B. And these are the allowed states for the SEP theory. And correspondingly, we'll generate some set E from this set omega SCP. Now, on the other extreme, we have some which we call set bar theory, where effects are limited, but the states can be generated from these effects. And somewhere in between, we have our usual quantum composition, where the effect space is basically set of all positive operators, and the state space is again set of all positive operators. So here when I say the state space, I'm talking in terms of unnormalized states. So we can easily see that there are actually infinitely many other theories possible in between. So yeah, I'll go towards this diagram in a bit. So here we can see that there are infinitely many possible theories in between. So yeah, let's go into this diagram. I'll explain it. So as you can see, for SEP, the states are very conserved. So only product states are allowed. Somewhere in between, we have quantum, and SEP bar have all kinds of states, very exotic kinds of states, which are not present in quantum. And similarly, if you look at the allowed effects in these theories, then actually quantum mechanics turns out to be such a peculiar kind of theory where the state space and effect space actually coincide, because the states as well as effects both are set of positive operators on HA tensor HB. So this is an overlapping picture here, exactly overlapping picture. But for set bar theory, again, the effects are restricted, and similarly, we can see the opposite for SEP theory. So, and as I said, we can consider many possible infinite combinations in between here as well as here. So I'd like to point out one result by Burnham and his collaborators. So what they showed is that local quantum mechanics, that is this local quantum measurements and no signaling actually imply quantum predictions. Other way of saying this is, let me elaborate it. So if we look at the standard bell scenario and play the bell game, so any correlations that you can achieve by any state from any of this state in this theory, it has been shown by Burnham that the same thing can be simulable by quantum mechanics or just by this quantum states and effects. So let me discuss briefly. So this result has been discussed in terms of space-like correlations. So let me discuss briefly what space-like correlations are. So suppose you have this blue semicircle denotes some preparation and the green semicircles denote some measurements. So some preparation has been performed and it has been sent to Alice and Bob, who are space-like separated. And depending on some inputs given to Alice and Bob, which are X or Y, they generate some measurement outputs A or B. And we generate this PAB given XY, which are known as space-like correlations. So what this result actually showed is that any bipartite space-like correlation obtained in any of the composition is achievable in quantum. So if the quantum, if your system satisfies the no signaling conditions, then beyond quantum space-like separated correlation, we cannot see. Everything that we see is available in quantum. So this space-like correlation experiments won't actually help us to make some distinction. So that is where this work comes in. And we move on to what are known as time-like correlations. So as I said, this is the standard space-like correlation, and a time-like correlation is something where Alice is actually preparing some system. It could be some composite system, but we won't assume what kind of composition is present between the system. And she signals it to Bob, where Bob measures something on the system, depending on what input he is getting. And then they generate this kind of correlation, which is known as the time-like correlation. So we'll see that in this time-like scenario, actually, we can make some distinction between all kinds of composition. So to do that, let me introduce this game, which we call the pairwise distinguishability game of n variables. So here, basically, we have some referee who will send some message eta out of this message is sent from some well-known set of messages. The set is known to all parties. So one particular message is sent to Alice. And a question is sent to Bob. So the question is some message eta comma eta prime, where this eta and eta prime are different, but both belong to the same known set. Now, Bob's task is to actually guess, depending on this question, which message was actually sent to Alice, whether it was eta or eta prime. And depending on what message Alice receives, she is allowed to encode this message in some state of some physical system and send it to Bob. Now, Bob might do some measurement on this system and conclude that the state is eta tilde, let's say. So the winning condition for this game is that, okay, so this is the pre-known set. Okay, this eta and eta prime belong to this set. And the winning condition for this game is actually that eta tilde should be equal to eta. Or another way of saying it is Bob exactly guesses which state was given to, which message was given to Alice. So we'll look into special kind of things where Alice has been given 2 elementary qubits to encode her message. So we'll answer this question. Will there be different success in this kind of game depending on what kind of composition is allowed to them? What kind of composition on local quantum systems is allowed? So we provide some affirmative answer for this. So before going into that, let me briefly define some definitions, which will be very helpful. So perfectly distinguishable states in some system S is basically some collection of states.
Just to let you know, so you've got about 5.5 minutes, including question time. So yeah,
5.5 minutes are left, right?
Yeah, including questions.
Sure. Okay. Thank you. So these are distinguishable states, and so basically perfect distinguishable states are those states which you can distinguish in a single shot measurement. And we have what is known as the operational dimension, which is basically maximal cardinality of set of states that we can distinguish. And pairwise distinguishability defines what is called as information dimension. So given some set, pairwise how many states we can distinguish. So yeah, I'll skip this. So let me show some observations. So for quantum theory, the information dimension and the operational dimension actually turn out to be same. It's very easy to see. And for this particular kind of game that I discussed, we can see that to win this game perfectly, we have to encode our states in, we need n perfectly distinguishable states, pairwise distinguishable states. So, that's it. That another way of saying that is if we have to play this game PDN, where n corresponds to the set of messages, the number of messages in the given set. If we want to win this game perfectly, then we should ensure that the information dimension of the system which we are using should be at least. So we'll consider this particular kind of game, PD12 kind of game. So if we restrict to quantum mechanics, we choose some states like this, where Z corresponds to the positive eigenstate, up eigenstate of sigma Z, and Z bar is the down eigenstate. So the best we can do in quantum mechanics is like this, because at most 4 states are pairwise distinguishable. And we know that this result from Zurek and Wouters, that since we cannot clone, so this is the best we can do. So in set theory, we provide an example of 12 states which are pairwise distinguishable. So, and as you can see, these states belongs to 2-qubit systems. So using this kind of 12 states, we can perfectly win this PD12 game. So 2 sub-bits suffice to win this game, but if you want to play this game with quantum composition, then actually we would need at least 4. Since the information dimension should at least be 12. So for 4 qubits, the information dimension will be 16. So why this is so? So this comes from a striking feature of this set theory, which was actually reported in this paper by Hayashi and his collaborators. So which is to say that non-orthogonal pure states can actually be distinguished in this set theory. So given 2 states, we can see that these 2 effects, which will actually constitute a measurement, are valid effects in the set theory because they give positive probability on all product states. So that's why these 2 effects can actually be used to distinguish these 2 states which are non-orthogonal. And this actually gives us the power to win the game, PD12 game. So I'm not going to discuss the rigorous proof here, but it's fairly straightforward. All we have to do is construct such measurements so we can distinguish all 12 such states. And finally, I'd like to give some theorem. So if we play this PD12 power k game, so in this kind of game, it's easy to see that this many quantum qubits are required, but 2k subqubits are sufficient. So the proof is fairly straightforward, but the implication is nice. So thus using set kind of game, this particular game, we can win by just 2k bits, and for quantum it would require at least this much. So there we can see that the difference actually increases linearly, and we have also seen that this strategy which we are using for the set kind of composition is actually not optimal. But if we use some optimal strategy, then we can argue that the difference will go even larger. And this is actually the plot of the difference. So what are the implications? So out of all possible such theories, we can immediately ask this question: what kind of theory should we select?
Just to let you know that we're running out of time.
Sure. I'll move on to conclusion. Sure. I'll move on to conclusion then. All right. So as I was saying, so we can immediately ask this question: why can't we take any possible theory in between as a valid theory? And this result actually helps us to answer this question, that actually such kind of games will give us some experimental scenario where we can test what kinds of compositions are allowed. So we take a stand that such games cannot be won, this n greater than 4 games cannot be won just by 2 qubits. And this helps us define which kind of composition to select. And similarly, we can extend this argument for 2 power k, n greater than 2 power k. So I'll like to conclude by saying that this bipartite compositions admit stronger than quantum correlations in time-like domain, and which was actually, we knew that in space-like domain such kind of thing was not arising. So in time-like scenario, we have actually made some distinction. And actually some previous work have been done in time-like scenario by Larno. So where they actually study what is known as the no hypersignaling principle. But the elementary systems there used were non-quantum in nature. So the result which we have provided, it strictly makes some statement on the kind of allowed composition of the qubits. So lastly, it would be interesting to answer how to omit all other kinds of theories. So what we have actually shown is a particular example of theory which can be excluded, but it would be interesting to answer how to exclude all other kind of theories and narrow ourselves towards the quantum composition. So that's it. Are there any questions?
That's great. I really enjoyed the talk. Thank you so much. I'm afraid we are a little bit behind time, so we don't have time for questions, but I remind everyone that
That's fine.
we can all discuss things in the break room after this set of talks. Tian Zhang, are you here?